Okay, so good afternoon. So we were here last time. We discussed optimization model for the neural networks, and we recall that the samples were given by this. So X1 are the features and YIs are the labels. And last time we saw that we can formulate this as an optimization problem where we compute the loss of the output from the network and then the actual output that we should get. So define a loss over that. We define a average of that. So divide by the n. So that is the global loss function that we define, and we need to solve this for the weight W. Okay. So weight W contains all the weights. So we saw that it's an unconstrained optimization problem. Okay, because W has no restriction here, and to solve this using gradient descent method, we need to compute the gradient. So gradient method does require a gradient. But apart from unconstrained, it also it's well known that it's non-convex. So this is a non-convex optimization problem, okay, and non-linear. Okay, so it's like not even quadratic. Okay, so this is the problem when we are working with neural networks. So we may apply the usual gradient descent method, and for that we need to compute the gradient. Okay, and the problem while computing the gradient is that it involves the f function, which is the neural network, and it's a nested function. Okay, so it's activation, then a linear combination, then activation, and so on. So it's a lot of nesting happening there, and within this nesting you have weights distributed. So computing a derivative of LW with respect to the weight, that is computing the gradient, won't be that easy, right? Because of the nested nature of the function. So main difficulty in neural network is that even if you know that it's not really a constraint problem and so on, but then computing the gradient is the main challenge here. And last time we also saw that we can write the usual gradient descent, but then we also introduced so-called stochastic gradient descent. And the reason why it is stochastic is because we are running, we are computing the gradient only over some of the samples. Okay, not really computing all of the summing over all of the samples. Remember that the actual loss was sum over all. Okay. And also one thing you note that Z and L is the same thing for us. So we could have also written capital L here, and theta stands for the weight W. Okay, so in this case, the problem was to minimize theta, minimize over theta, J theta. So this was our problem, and we are trying to minimize this over the M samples here. Okay, so originally if I had to do this, then yeah, so here M stands for the complete set of samples, but here you should not get confused that here M is the selected set. Okay, so here, like I did in the previous class, maybe I should use a N. Okay, N. So N is the small subset of the set X1 to XM. Okay, so X1, X2, Xn. This set is a subset of the global pool of the samples Xm, small m. Okay, so we are taking only a subset and we are defining a loss over the subset. So we are defining a loss over a subset of original samples. Okay, so and then we are also usually we take this randomly. So which of the n I will choose is random. So pick n samples randomly. To get a so-called mini batch that I'm talking about here. And that is the reason why, first of all, it's a partial gradient because I did not compute the loss over all the sample. And the second thing is that I've chosen these samples arbitrarily. So that's why it's a stochastic. So it's not really the full gradient, but it's now a stochastic gradient. Stochastic gradient. And this is the usual process that we recall. So theta is theta minus epsilon times the gradient. And then there are many heuristics to choose the theta to the epsilon. OK, so at each iteration k, so you imagine that this gradient descent is running for k iterations. So then you can define different step sizes for different iterations. OK, so one of the way to define is this way. As I said, there are heuristics, so you may encounter many different types. So you can, for the moment, like you can just take something like this. OK. OK, so usually when you run the gradient descent method, so in this case we have the level curves. So that's why it's a 3D function, but we can plot this in 2D. That's the goal of level curves. And then it can start from somewhere here. So this is the starting initial guess. And then it will end up somewhere here, right? So so it's an iterative method. So you will start from some initial guess and then it will iteratively it will go there. How fast or how slow it goes there, it depends, right? OK, so the following shows the gradient descent method applied to Beal's function. So there is some functions for two initializations. OK, so in this case, let us say some initialization is there, which is 2 minus 2. This is one example where I am computing this, and I may also start with this. Maybe I have not. Yeah, so this is another initialization of minus 3, right? So here I'm talking about another. So here I could have started from here. So minus 3. As you know, starting from different places, here you started, so you were going rather more closely. And here your initial guess was bad, so it will take some more time to reach there. OK, so this is just an animation. Actually, you can click on this and later you can see. OK, there is an change there is some update on this. So there is a further modification to stochastic gradient descent. It's called SGD with momentum. So the idea here is the following. So set v is equal to 0, alpha, choose alpha some parameter between 0 and 1. Usually it's chosen to be 0.9. Compute the gradient g like this. So compute the gradient g and then update v like this. So v is alpha v minus epsilon g. Epsilon in the step size. So assuming that you choose some appropriate step size, then the gradient step that you compute will be given by this. OK, so what is happening here compared to the usual SGD? If you see the usual SGD here, in place of v, we were having just epsilon g. OK, in usual SGD. OK, but now instead of epsilon g, we have epsilon v minus epsilon g. Sorry, alpha v minus epsilon g, right? So there is a slight change here. OK, so this is the changing part is this part, right? And so the original update of the stochastic gradient descent would look like theta minus epsilon g. And then in the momentum, what we are doing is the overall what we are doing is theta minus alpha v minus epsilon g. OK, and it's plus here. So this is what we are trying to do. OK, so so this is the momentum based method. So the question is, why did we do this, right? The idea here is like this. V, if you can see here, V is like an average of your so V is accumulating the gradients, right? So if you run to the second iteration, the first iteration V is 0, so nothing will happen here, right? So the first iteration V, let us say I denote V0 as the first iteration V, that is 0. Okay, so V1 in this case will be alpha 0 minus epsilon G. Okay, and then V2 will be alpha V1. Okay, so that's how it is given, minus epsilon the current G, right? So let us also call this G1, and this is the gradient with G2. Okay, so but yeah, so here alpha V1 we substitute from here, so this will be minus epsilon G1 minus epsilon G2. So this is minus epsilon G1 plus G2, right? So the current V2 that I get is a kind of a average I can think of, because it's G1 plus G2. Okay, so I'm keeping hold of the old G1, and then I'm adding it to the current G2, and then I'm doing the update.
So there is additional alpha, right? Alpha G1.
Yeah, there is additional alpha also. Yeah, so here we had alpha times V1, so there will be alpha also here. Yeah, so there will be alpha here. Okay, sorry, okay, now it will not work. Okay, so there will be alpha here, alpha. Okay, so here also there will be alpha. Okay, so alpha will be like somewhere inside actually here. Okay, let me correct this. So V2 is this. So then alpha, and then yeah, so V1 so V2 will be minus epsilon alpha G1 plus G2, right? Okay. Now, depending on alpha, it will determine whether how much importance you want to give to the previously computed gradient. Okay, so that's the thing here. So alpha gives you another hold of how important it is. Like for instance, here I'm giving 0.9. I'm like 90%. I want to take the historical information of the previous gradient. Okay, one would have meant that I want to consider the previous gradient as important, but here, so it's a hyperparameter, obviously, depending on different things, it will vary, right? So overall, what we see is like the update compared to the usual stochastic gradient methods. So this will be theta plus, and so it will be like minus now. Okay, so let me delete this. So this is theta, and then minus epsilon alpha G1 plus G2. Okay, so what we observe is that instead of taking G2, now we are taking alpha G1 plus G2. Now, if we apply this recursion continuously, I will have more and more. So in the next time, I will have alpha square G1 plus alpha G2 plus G3. Okay, so this way recursively it will keep. So since the alpha is less than 1, alpha square will be more or less than 1 compared to alpha. Okay, so alpha square will be like 0.89, right? 9981, right? Yeah, 81. Okay, so it's like 0.81. 0.81. Okay, so you're saying that you want to take 0.81 of the G1, and then you are saying that you want to take 0.9 of the previous one, and then 1 of the current gradient. So overall, the intuition behind this is that rather than taking only the current gradient, you take some kind of a average, weighted average. Okay, in the sense that the most recent one will be given more weightage, higher weightage compared to the previous one. So as you are going ahead in future, you are giving less and less importance to the previous gradients and so on. Okay, so why all this, right? So why should we do all these things, right? So the idea here is the following. Momentum is especially useful on a tilted surface with high curvature. So this is an example that is given to you. It's high curvature, okay, because there is a lot of bend here. Second derivative is like very high. So stochastic gradient descent may make steps that zigzag. So this may happen especially in this kind of problems where you have high curvature, and this is very much prominent in neural network based functions. So if that is the case, then if you follow the usual gradient descent, then you will start with some initial guess, let us say, and then it will throw you this way, okay, and then it will throw you this way, and then again it will throw you this way. So you are oscillating a lot, okay, and this will slow down your progress. So oscillations are the same thing as saying zigzag. Okay, so to make sure that you don't get into too oscillatory behavior of your progress, you may want to take some kind of average. Okay, so that will help, right? So if I want to, so this direction was this way and this direction was this way, right? So one direction is this way, okay, and the another direction is this way, right? So another direction is this way. So I want to go into the average, so I will add some way, right? So I will add the previous two directions. Okay, so that will be the average direction that I want to go. Okay, so this way I maintain some kind of average, and then I don't oscillate too much. Okay, so that was the idea behind momentum, that you on a very oscillatory functions surface, especially those generated by the neural networks, you may want to use the momentum to prevent this oscillatory behavior. So if I write down what I have also explained like this before, and then I have computed V1, V2, Vt. So Vt will look like this, where there is a highest power on the oldest gradient. So as the iteration increases, lesser and lesser weightage is given to older gradients. So that's the intuition behind this, because you want to see that you want to see the recent oscillatory behavior, not the very old one, right? Because you may have progressed into a surface where older gradients are no longer important to understand the oscillatory behavior. So you would not like to give more prominence to very old gradients. Okay, but all this depends on what parameter alpha you choose. So momentum helps in also taking large steps, because rather than doing the oscillatory behavior, your direction was to go here, but then since you are oscillating a lot, your average direction should have been this way. But since you are oscillating a lot, you are moving very slowly. So by doing a momentum, you will move much faster rather than oscillating. So helps in taking large steps in the region of gentle slopes, and it helps in taking the large steps because because I'm not that afraid now, because if I use the original gradient descent method, then taking a large step is a bit problematic, because that was not the correct direction and then I took a large step. So I went in a very bad direction somewhere here. Okay. So that may be very far from my actual direction. So, but then if I'm doing the momentum, then on average, since I'm keeping track of average, so I believe, okay, again, this is an intuition again, right? So on average, we believe that this was the correct direction to go. So I could have taken larger time step. So I could have reached directly here by using the average of the previous ones. Okay, rather than doing too many oscillations. So so we are, in some sense, we can take larger steps and we don't get off track. Okay, so that's even in the region of gentle slopes. However, the momentum based methods usually overshoots the valley. So momentum based method may also, obviously it may also overshoot the valleys, because what may happen is, in this case, in this example, if you can see, it starts from here and then it overshoots, right? The reason why it will overshoot, I can explain you maybe shortly. Yeah, so this part I will explain you. So far what we were thinking about is that oscillation is a problem here. So it's rather take an average to avoid the oscillation. But then what we are trying to say is like, if you go via momentum based idea, you may overshoot also. So the intuition behind overshooting is that if your history is always of one type, okay, so let us say if your history was always to decrease, and since you are keeping an average of only decrease and so on, so it may happen that you were close to minima, but then since you took so much of the historical information of decrease that you could have reached to minima, but then since you are taking average of all the decrease, you will overshoot. Okay, so that's the problem here. Okay, I will explain this in the next slide again. So indeed, this is what happens in this example. Observe now how it comes back. So it will come back because that's the goal of gradient descent, that even if it overshoots, let us say for the moment assume that it overshoots, but then gradient as such, the gradient will pull it back because gradient will always point to negative, gradient will always point to decrease. So even if it overshoots, it will be brought back. So that's fine. But then why would it overshoot, right? So it may overshoot and then it may look like this. So if you focus on this figure here, then it overshooted. Okay, the minima is somewhere here. So it overshooted and then it was brought back. Again, it overshoots, it brought back, overshoots, brought back, and so on. Okay, so again, momentum-based gradient method makes so it may still be oscillatory, obviously. Okay, even though you are going on average direction and so on, but then the point is, as I said, if you are using momentum-based method, and if somehow your history has been to decrease for a long time, right? Then you will overshoot again. Okay, so but what matters here is that it will still converge, okay, faster than SGD, is because SGD oscillates a lot. Okay, and momentum also has the possibility to oscillate. Okay, when it is very close to minima. Okay, SGD can oscillate even outside minima, but momentum may oscillate when you were close to minima and then you were still adding momentum. Okay, so that's the whole idea of momentum, right? So if you are like in a ball-shaped curve and then if you throw a ball, right? So the main idea of the momentum-based method is that you are using the momentum. So since you are using the momentum, you let the ball fall, it will go here. Okay, so it will go here and then it will overshoot. But then gradient method will make it come back. Okay, so it will come back and then it will overshoot. So you will see that it will go like this and then finally it will settle. Okay, so that's the problem with momentum based method. Okay, so and also another thing is like it depends obviously on the starting point, but SGD also depends on the starting point. Different. I mean, this is just a example. Okay, that if I started from different starting point, SGD is going in some other direction. Momentum went in some other local minima. This was the global minima. Okay, so this is the global. So these are just some cases. Okay, there is no absolute guarantee, right? There is no absolute guarantee that even SGD will converge to global minima, and the momentum will not. Okay, so either way can happen. Okay, so but this was just an example to show you that although you started from the same initial point, SGD is looking like it's going to the global minima, which is the star, but the momentum based method went into some local minima. Okay, and it stops here. Obviously, we know that SGD only guarantees local minima in the non-convex case. Okay, so
Hello,
yeah,
sir.
so yeah.
Sir, if we reach to a minima, although SGD plus momentum will move, right? Like it doesn't converge, right? Because the previous gradient effect will be there.
Yes. Yeah, previous gradient effect will be there, but those effects are less and less due to the alpha power that is decreasing as the iteration count is increasing. So So you may take more time, but the fact that previous gradients are forgotten also. So that's why on average it will converge. Okay. So as I said, like there is an advantage and disadvantage also. What is the disadvantage here? This is the graph that is telling you the disadvantage. So if your accumulated history of the gradient, remember that in the momentum method, what do? We accumulate the gradients, right? Although we accumulate it in some power, right? So alpha t minus 1 epsilon g1 plus alpha t minus 2 epsilon g2, okay, epsilon g2 and so on. Okay, and then the recent one does not have, so it's just epsilon g gt, right? So the recent one doesn't have anything to do with that. So in the momentum based method, you are adding these additional gradients, right? So what if your gradients were always in the decreasing direction, right? So here the moment was decreasing. Here my moment was decreasing. I mean the gradient was in the decreasing direction. So it's all negative, negative, negative. So it's like I am close to the minima here now. Okay. So this is my, let us say, optimal W star is the optimal. Now, since I am coming closer, my step size should have been smaller and smaller because now I am very close to the minima. So I should not go, I should not go too far. Okay, so if I take a very big step size, let us say I'm here. Okay, the gradient is pointing this direction, and if I took a very big step size, then I will end up here. Okay, so if I end up here, then I overshooted the minima. Okay, and then I will compute the gradient again, and then the gradient will pull me back. It will say that, well, the minima is somewhere here. Again, I have to go this direction. Okay, so if I took some step size, let us say, then I will reach somewhere here, let us say, and then I plotted the gradient again. And if I took the step size a lot more, then I arrived here. Again, I overshooted the minima, and then I came here. So this thing may keep happening. Now, so that's dependent on the step size. But then in the momentum based method, so one possibility in usual gradient descent method is that you decrease your step size as the iteration is increasing. Perhaps you are already close to minima. So then you have to be a bit careful and move slowly towards the minima. Okay, that's one lesson. That is for the usual SGD. But in the momentum based method, the additional thing that is happening is that we have the previous gradients being added. So if the history was to decrease, and then if I'm here, I am adding more decrease from the previous history. So this has the tendency that I will overshoot again. Okay, assuming that the epsilon step size was not touched. So there is a possibility that I will overshoot because all my this previous gradients will get accumulated. So and then they will make a lot more decrease than the usual SGD that would have done small decrease. Adding so many decrease will make it a lot more decrease. In other words, I will overshoot in that case. Okay, so there are advantage and disadvantage also. So in this case, I will overshoot and then I have to come back and so on. So of course, like one may introduce some adaptive step size to ensure that the momentum based method does not overshoot because of its accumulated history that maybe have only one trend of decrease. Okay, so we may see some update on this. So if I see so one more variant of the momentum based method. So there are like SGD, and then what we saw is SGD plus momentum. Okay, so that's second one, and the third one is SGD with Nasdrov momentum. So the momentum are of two type. Okay, so there is one Nasdrov momentum. Nasdrov is the Russian scientist who proposed his own variant. So what he did is, remember that the original SGD with momentum was V is alpha V plus epsilon G, and then theta was updated immediately like this. So these were the two steps, theta plus v. Okay, I think there was like minus or plus. Don't worry about those things. Signs we can always like, yeah, this is minus. Okay, so don't worry about sign because it's about rescaling things appropriately. Okay, so that's fine. I think I choose a plus here instead, and previously I chose minus. Okay, don't worry about that. But okay, so so what matters here is like if we, so this is the momentum, but then what Nasdrov said that rather than computing this gradient on the previous theta value, actually you update actually you add that alpha times v and then compute the gradient. Okay, so here the g was computed on this was grad theta j theta on theta only, right? So this g was computed on theta, but what Nestor did is a simple extension to this. What he suggested is like you update theta by alpha v and then compute the gradient. Okay, and so compute the gradient already at a new position now, and then you have a v. Okay, so this was the original momentum based method, and what Nasdrov suggested is compute now at theta plus alpha v. Okay, and then you change your v like this and now update the weights. Okay, so there is this slight change for the Nasdrov case, that you compute gradient on the updated value now, updated theta. Okay, not on the old theta. So this is the slight change in the Nasdrov, but it turns out that Nasdrov and Nasdrov with momentum actually work in a very similar way. Okay, it's just that one step, it may be one step faster. You can think like that. Even there is no concrete guarantee, right? So because these are anyway like stochastic methods, so on average we talk about always about on average whether it's converging or not. So whether I did update now or in the next previous step, the maximum you can expect one step faster convergence. Okay, so in practice, what I'm trying to say is like they converge in the same way. Okay, so it's a very similar convergence. Okay, so these are some plots. You can click these animations later on, so I can skip this. One may introduce adaptive learning rate. So as you have seen in momentum based method, there is a possibility to overshoot because your history may have been to, let us say, decrease, and then you are close to minima, and then you have thrown in more decrease from your history, and then you will decrease even more. In other words, you will overshoot. Okay, more than you will do more than necessary. So in the beginning, a larger running rate is typically better because you expect that your guess was very bad. So you may want to proceed rather quickly, but then when you are near, you have to be careful. Okay, that's what I explained, right? So as time goes on, epsilon may need to be small to be able to make appropriate updates to the parameter. Okay, so apply some decaying rule to learning then. A common form to anneal or to decay the learning rate is to do so manually when the loss plateau or to annihilate if after a certain number of epoch of the gradient descent. Okay, so we may do this manually. In the one possibility is like we, depending on the number of epochs, we keep decreasing it. Okay, so for instance, it could be learning rate could be 1 by t, where t is the iteration number. Okay, so the first step it will be 1, second step it will be 0.5, and then so on, 1 over yeah, so 0.2 and then so on. Okay, so adaptive gradient is a form of stochastic gradient descent where the learning rate is decreased by whatever way you want. For instance, in AdaGrad, there is another update to gradient descent methods, which is called AdaGrad. In this case, you apply that adaptive technique where you divide by the historical gradient norms. Okay, so again, these are heuristics. So you divide by the historical gradient norms, which is like this. Okay, so this is yet another gradient descent method, and the way we do updates are like this here. So you compute the gradient, and you compute. So you compute like pointwise multiplication of the gradients. Okay, so there is a pointwise multiplication. So G1, G1 square, G2 square, and so on. Okay, and then you update the vectors. Okay, and then this is also pointwise multiplication with this alpha, sorry, epsilon, and so on. So this is looking like in a different form than what momentum we were doing here. So here, what kind of momentum we are taking? It's the type of momentum we are taking is of the form of square of the gradients, right? Right. So the type of momentum we are taking here is square of the gradient. Like, so why would one do square, right? So that again looks like some intuitive things. Previously we were only talking about gradient, but now it's like a second order approximation being done here. Well, second order would be Hessian, right? So Hessian will be what? So Hessian of our loss function, let us say f. So it's like a double here, right? Okay, so this is f. Okay, and let us say this was the neural network with this weight theta. So in the second order method, instead of gradient, you take a Hessian. Okay, you consider Hessian, but then Hessians is not easy to compute. So del 2 f by del theta. So theta is a vector of components, right? So it's like theta 1 square and so on. 1 square and del 2 f by del theta 1, theta 2, and so on, right? So this is a matrix like this. So one possibility is that I consider a diagonal approximation to this. Okay, so diagonal approximation will contain this type of terms, right? Second derivative terms. So this is kind of a approximation to that. Okay, so like kind of second order information you are trying to take, but still this is a bit different from this. So del 2 f by del theta 1 square is not equal to del f by del theta 1 whole square. What we are really computing here is this kind of terms. So it's a kind of approximation in some sense being done here of the second order terms, because second order terms capture more information. So you approximate, you take second order kind of gradient approximation to that, and that too is not the proper Hessian, but just the diagonal term. And then you define, so this is the accumulated, you can say the square of the gradients. Okay, and then you update like this. And one more thing is this is the adaptive gradient, right? So this is the adaptive step size, right? Because this keeps changing, right? So E will keep changing based on the second order information. I'm trying to scale my my step size. Okay, and then I have this this G term here. Okay, so this is being used. This is being used to estimate the step size or to scale the step size in a proper way. Behind this is like, if there are a lot more oscillations, then these guys will be like if the curvature is getting very what to say, if the curvature is getting very high, then my step size should decrease, right? So if my curvature is like this, okay, then the second derivative will be very high here. If my curvature is like this, then the second derivative close to this point, let us say I'm going in this way, the second derivative will not be that high. So so I divide by proportionally lesser magnitude term, assuming that I have a second derivative estimate in the form of this. So second derivative is like square of this. OK, so these are like all heuristic because I don't want to compute this second derivative. OK, so what this intuitively suggests is that if my curvature is a lot more and if I am somewhere here, OK, so if I'm somewhere here, if my curvature is so if I'm here, then it seems like my second derivative is going to be very high. If that is the case, then my step size should be small. So I'm dividing by that that quantity here. OK, so I'm dividing by that quantity here. And one more thing to note is like this is a vector. OK, this is a vector. Square root of a plus nu is a vector. So it's like component wise, I am multiplying g component wise with 1 divided by square root of a plus nu. OK, so this tells me that if there is a certain direction along which, let us say theta 1 is the direction along which there is a sharp curvature, then steps I must like decrease my step size proportionally along that direction. OK, so that's what it's trying to say because it's a pointwise thing, right? So this will be like g1 divided by square root of a1. So the first component plus nu, and then there is a epsilon here, and then epsilon g2 divided by square root of a2 plus nu. Nu is some again hyperparameter. I mean the nu is a hyperparameter in the sense that it may happen that sometimes this some components are 0. To make sure that it's not divided by 0, you add some nu. So this is here to prevent division by 0. So this way we have this this vector here, and then OK, so this is the whole thing I've written here. OK, so what we are trying to say is like if the curvature is very high along certain components, so this is the theta 1 component, this is the theta 2 component. OK, so if the component is very high, then the corresponding a1 will be very high because that more curvature will mean more a1, and that would mean that I have to slow down. OK, that would mean I have to slow down. So automatically the step size along that direction will be slowed down. OK, and then if along other direction I am not very curvature is not that that much, then I may move that component more. OK, so this is again a heuristic. You can say you can first heuristic. It is heuristic is because there is no guarantee that del 2f by del theta 1 will approximate del f by del theta because the actual curvature is given by this. And what we are saying is that del f by del theta 1, because that is the g dot g will pointwise will mean del f by del theta multiplied, right? Because g contains del f by del theta 1, del f by del theta 2, and so on. So g pointwise multiplied with g will mean del f by del theta 1 squared. So first, the reason why it's heuristic is that first of all, curvature is given by this, but we are saying that this may be equivalent to this. So that's again a heuristic. There may be someone may come up with a counter example and say that, well, there are cases where it's not, and then this will not work. Obviously, SGD, many of these are heuristics. Again, I'm saying, OK, so there, so I may prove that for certain class of problem, this is good. So you should go with ADA grad. So there are certain cases where you should not use this. OK, so these are the intuitive ideas behind ADA grad. OK, again, like I will not claim that this is a sure sort thing for everything, right? As I said, these are heuristics, and you will always come up with an example where ADA grad will do very bad. OK, OK, so yeah, so the step size may vanish, and that's why I said that we add this parameter, a very small quantity. We should be very careful that we add a very small quantity just to make sure that there is no a doesn't become 0, because it may happen that along certain direction the derivative is 0. So del f by del, for example, del f by del theta 2 may be 0. OK, so in those cases we make sure that it's not divided by 0, and we have the algorithm actually works. So there are few other intuitions of ADA grad, and And they are the following. Let us see. So let us say that your prediction function is like this. OK, so fx and then 1 by e to the. So this is the usual. You see the sigmoid and so one perceptron, right? So this is the perceptron thing, and then let us say theta 1, theta 2, and then we took a linear combination, so x1, x2. So this is this theta transpose x will look like theta 1 x1 plus theta 2 x2, and then we arrive here, and then we do the sigmoid activation of this. So sigmoid activation of this sigma sigmoid of it depends which type of function you think of, right? So this will be 1 divided by 1 plus e to the minus theta transpose x. And then we also add the bias here. So there will be bias here plus b. And this is the, so this is one perceptron neural network. And that's the how the function neural network looks like. So I see this as a function of x during testing because I'm assuming that theta is known, so that becomes a constant. But I could have also seen this as function of theta during training because then sample is known and then I'm tuning x theta, which is unknown. OK, and so if I take, so let us say that it's a function of theta for the moment. So then grad f, so I mean a grad f here. So theta has, let us say, two components. OK, like here, theta 1, theta 2. So if I take a gradient with respect to theta 1, OK, it's an easy task for you to prove that if you take a gradient with for the sigmoid, this is how it looks like. OK, and then if you take a gradient with respect to theta 2, this is how it will look like. So what is happening here, right? So if x squared happens to be very sparse, not x squared, but I mean x2, the second component. OK, so if x2 happens to be very sparse or small, then the update for W2 will be very small, obviously. So if x2 is small, then the update for W2, OK, sometimes I mix W2, sometimes I mix theta 2, so I have to be very careful. OK, so what this is saying, if x2 is small, obviously the gradient will be small, and if the gradient will be small, because for theta 2 the update will be old theta 2 minus grad theta 2 of f. OK, so so this is how the update will happen. So but since x2, the sample x2, so this sample x2, if it so happens that the sample x2 was a very small value, OK, the feature is very small, so that will make my gradient very small. That would mean that the second component of my weight, OK, so my weight has now two components, right? So this is like a theta 1, theta 2, and in the gradient method I do old theta 1, old theta 2, and then minus grad theta 1 f and grad theta 2 f, and then some learning rate also you can put here. So we are now looking at component wise updates that is happening. So if it so happens that x2, the second sample, is small, that will make the second component of the gradient small, meaning this component will be very small. So the update to theta 2 will be very small. OK, because theta 2 will be approximately theta 2 only because there was nothing coming from this. So if this feature x2 was not important, let us say, if this feature was not important, look, small value of x2 does not necessarily mean that the feature is not important. OK, that feature could have been still very important. So but so if x2 was not important, then it's not an issue because then yeah, anyway, like anyway the update, we don't really care about the update based on that feature x2 because x2 was not really that important feature. So if I'm building a neural network model for housing price predictions, then maybe let us say a few things may not be very important, right? So for instance, maybe let us say let us say the second balcony may not be that important, provided the first balcony is big enough. Second balcony, people may not care, right? So second balcony area size may not be that important, right? So in that case, that feature could be x2, and that is not really an issue. So I don't really want my model to learn something about that feature. Okay, so my second balcony area. So that's not an issue. But if it may happen that it was actually important, but it was given smaller value because when you are collecting data, scalings is not something you know about, because there are relative scalings, right? Because there are some units where you do things in a different way. There are some, because number of bedroom will be 1, 2, 3, something like that, and the area will be in feet. Then you will do it in some scaling. If you do it in meter, then it will some scaling. So some values being less doesn't mean that it's not important. So for example, 1 bedroom house. Okay, so the value for that feature will be 1, right? So let us say I make a feature matrix x1 and x2. So this is, let us say the number of bedroom is 1, and let us say this is the area of the bedroom. So let us say this is like 2000 square feet, right? So it doesn't mean that I'm going to neglect this guy, right? So I'm just giving you an example here that compared to this, I may not be able to neglect this, because 1 bedroom is important feature. Okay, 1 bedroom or 2 bedroom is really another important feature. So um, so so there may be smaller values for some feature, but it doesn't mean that I have to neglect that. Okay, so in some cases I have to give prominence to that. And how do I do that? Right? So how do I do that? So, but if it was important, how could this be corrected? So what we should do, we should amplify, right? Because if we go by the usual gradient descent method, what will happen is that by the nature, it's a numerical algorithm scheme. So it doesn't know what I meant by bedroom, what I meant by square. For it, it's just a numerical data, and it will see that, okay, this guy is very small, so gradient computed will be small. So it will be, model will be giving less importance to updating the weights corresponding to that feature. If something is important, then the weight should have good changes accordingly, right? But then in that case, if the value is already small, the weights of the model hardly change. Okay, so that is not what we want. If the bedrooms were 2 and 1, which are still relatively very less compared to this, I want my model to strongly update the weights if it goes from 1 to 2, although 1 and 2 are still very small compared to this. Okay, so how to correct this? Well, we will amplify certain corresponding to certain features. We will amplify the gradient and implying that we want our model to put more emphasis on those weights also. So to amplify the weight, we take the step size proportional to the inverse of the accumulated gradient. Okay, so that's also a added advantage. Okay, 1 + 1 advantage here. Okay, so you get 1 free for. So so this is another motivation behind using AdaGrad, in the sense that I am trying to amplify those components for which the gradient was coming out to be small. Now remember what was A, right? So A was the accumulated gradient square, right? So this is like del f by del theta 1 square, right? So the components of this. So A1 was like this. Okay, there were some previous A also term added here. So I'm not writing that, but it's like this roughly. So if the gradient with respect to, let us say, x2 is coming out to be small, then this guy will be small, right? So if x2 is small, then this implies grad f theta 2 is small. So this implies grad f theta 2 squared also, because A contains the square of that. So grad f and del f by del theta 2 is the same thing, right? So this is also more small, right? Is small. So to make sure that that part of the update is not lost here, I will divide by the small part here, right? So here I will put square root of, divide by that, right? So divide by square root of theta 2f. So if this is small, then it will magnify. 1 by small will become big, right? So that will amplify the second component now. Now the update will happen for theta 2. in a good way. Okay, so that got amplified. So AdaGrad, so what is the conclusion? Okay, so AdaGrad is a good solver to use when you believe that your data scaling is very bad. And some of the feature values are so low that it is important for you, but the values are somehow slow and you have tried all kind of mean scaling and whatever, but still somehow you believe that some data is very small, but those features for you are important. Then you may go ahead with the AdaGrad to reinforce your model in a way that smaller values are not ignored. Okay, so that's intuition again, why one may want to use AdaGrad. And as I said, the previous intuition also obviously holds here. So there are like two added benefits of AdaGrad here. Okay, the previous reasoning and then and also the cases where you have very small values for in the feature. Okay, so this is again animation for AdaGrad and so on. So if here you will see that AdaGrad is fast. So in this plot we have compared gradient descent with the momentum. So P is in physics, P is used for momentum. So similar way they also use P for momentum. And there is a Nasdrov momentum, which is NP, and then there is AdaGrad. So yeah, so you will see that SGD is still here while others are comparable. So they others. So GD is like a stochastic SGD actually. Okay, and then you have others. The other three are more or less equivalent, so they converge rather quickly to the global minima, while SGD is very slow. Okay. And then one can also do this with different starting points. So they behave differently. This plot is telling you that. So for instance, red one is AdaGrad. So AdaGrad manages to converge in this example, not always guaranteed. In this example, it is actually going to the actual global minima, which is star. SGD is going, but it is very slow by the time all others have done. But momentum based method went into some local minima. Okay, it's not a full proof that AdaGrad is always the best and so on. It's not a full proof, but it's just a example telling you that different behavior is to be expected. Okay, so at least for this example, AdaGrad seems to be the best choice because I wanted to go to global minima. I wanted to be fast. So and in this example, AdaGrad makes sense. Okay, again, there is no concrete set of things. Okay, people try actually many different things and then you do cross validation and so on. Okay, so these are even the solvers are kind of hyperparameter in the broad sense, but as I said, if you know a little bit about your data, for instance, if it's sparse or it's very small data, small feature data is important, then go for AdaGrad. Okay. If you know about the nature of your neural networks, it's very highly oscillatory and so on, then you may also go with Nasdrov momentum or momentum and so on. Okay, so there are many variants. So there is a zoo of these things. Okay, so people just try actually. Okay, but people usually don't use SGD in general. Okay, they always use some momentum or AdaGrad or RMS prop and so on. So RMS prop is a slight modification of the AdaGrad. You will see that the only modification that happened is here, and this is a weighted average you are taking of your previous accumulated A. Like A here, you will see that previously they were using V, right? So V was analogous to velocity. The velocity is like one derivative, first derivative, right? So this is like del F by del theta. And then they started using A. So A is like an acceleration here. Well, as I said before, acceleration would be del 2F by del theta square, but then they are approximating it by del F by del theta whole square, something like that. Okay, so you may object to this, but that's some kind of an approximation they're using. So you have an average acceleration going on now in RMS prop. So that's so this is average in the sense that you are doing beta and 1 minus beta. Okay. So, I mean, why exactly one does this? Okay, there are some kind of analysis going on here. I'm not going into that. So, and beta is also a heuristic here. Okay, so typically, again, you will argue that beta will be chosen to be less actually, so that you want to give more prominence to the recent gradient than the previous gradient that is accumulated in A. Okay, so but again one has to play with this, and the update rule is the same as AdaGrad in the sense that you have an adaptive learning rate. Okay, in fact adaptation is coming from the whole term here, the whole term here. In our original case, epsilon was the learning rate, but now this whole thing is a learning rate for us. And it's adaptive because the inner term is changing. Epsilon is still fixed, but inner one is changing, square root of A plus. So you can treat this as epsilon hat is the new learning rate, adaptive learning rate. And this is dependent on T. So we can also put a subscript T here to show the dependence. And one may try and do many things on top of this. You may do a hybrid, right? So you may do something like this. Okay, so it's like you are taking a acceleration, average of the acceleration, and then you are also taking some velocity term, and then you are updating like this. So this is like a hybrid again. Okay, so you may want to benefit from many things. That's the point. Okay, and again, these are like, I would say, intuitive overall, because it may not be guaranteed to work all the time. So you want to take advantage of acceleration, you want to take advantage of this, and you update rule is like this. So this will be called RMS prop with momentum. Okay, so and then yeah, so AdaGrad may decay the learning rate aggressively. So do not decrease the denominator too aggressively. So that is the reason why that was included. So you rather use the weighted acceleration. Okay, there is an animation again for different variants of these methods like RMS prop, AdaGrad, and so on. And in some cases, like RMS prop, AdaGrad went to the right global minima, whereas those previous ones are still going to the local minima, obviously, because the starting point is still the same. SGD is very slow. Okay, that's why people don't use SGD at all. Okay, so these are the RMS prop with momentum, and then there is now you could have guessed already by now, I could have made a nice melange of all the ideas that I have found so far, and then come up with something called ADAM. Adaptive also, momentum also. Okay, and so this is how we can define. So this is the average of the velocity. So this is like average velocity, and this is the average acceleration. Average acceleration, and then based on that you define your update rule like this. Okay, so okay, I think here isn't this something missing, like I updated A. Oh, okay, no, that's all. Okay, actually so it still remains V here, and that's the weighted V. The A was used just for an adaptive learning rate. Okay, so this was to make sure that adaptive learning rate is there, and V is the average V. V is the average of the gradient. Yes.
Sir, it is beta 1A, right?
Beta 1. This is beta 1A. Yes, you're right. Should be beta 1A. Yeah.
Or might be beta 2 only, I guess, because the first momentum also.
No, beta 2. Yeah, beta 2, because beta 1 and 1 minus beta 1 is taken care of. Similarly, beta 2 and 1 minus beta 2 is like proportionally which one I want to weight more, recent one or the previous one. Yeah, this is still beta 2. So here we have taken advantage of the momentum idea. So this V was coming from momentum, but then we tweaked a little bit. We took a weighted momentum like this, beta 1 and 1 minus beta 1 type, rather than just saying alpha and something. And then we also took the idea from RMS AdaGrad, and then took the weighted in that sense. So we took this from RMS prop here, right? So actually RMS prop here also was there, and RMS momentum also we had the same thing here. Okay. So and then we had this thing again, as I said, there's no guarantee that Adam will be always the best. So there are times where ADA grade will be good, where times where I mean, just the fact that you combine everything doesn't necessarily mean you are always going to be good. There will be cases where you will be good faster. There will be cases where you may not be good. So these are the So the overall algorithm of the Adam is like this, and there are some theoretical reasons that I may not be able to go, I guess, is so-called bias correction. So these were the previous steps: average velocity, average acceleration, and this was the last step that we saw. But then there is something called bias correction in the moments. So there could be a bias, and can you remove that bias? Okay, so can you correct? I mean, can you correct the bias in the averaging that you're doing of the velocity and the acceleration? Then the claim, there is a theory behind this. The claim is that with this bias correction, you will, you will converge to the expected gradient, something like that. Okay, so there is a concrete proof behind this. I don't remember exactly the proof of this, but I think, yeah, I have noted this down here. So let us see how the proof goes. If in V, we do the running average of the gradient. So that's the velocity. In other words, we are interested in the expected value of the gradient. So what we are expected in, right? These are stochastic gradients, right? And remember, there is they are all children of the gradient method, right? Gradient descent method. These are just modifications of their original method. And original method was guaranteed to converge to local minima because we were computing the full gradient. But in these variants, even the full gradient is not really computed. So in some sense, I cannot even guarantee that you will converge even to local minima. Okay, even to local minima guarantee may not be there because the gradient itself is stochastic. So it's not a concrete gradient, because actual gradient was pointing in the direction of decrease. I'm taking stochastic gradient. It may be pointing in a direction of maybe some other partial decrease, not the actual decrease, something like that. In fact, it may point in the direction of increase also, because I did never compute the actual gradient. So there is a danger that's why you will see that when you are running the machine learning models during training, sometimes your loss is increasing also. That will never happen in the actual gradient descent, because by nature it will always, of course, it may happen when you are close to the minima. Then you may do overshooting because of the learning rate and so on. But the stochastic gradient method, it may happen even outside the local minima, because your gradient computations are not good. Okay, because I may have a function like this, and the stochastic gradient method, if I'm here, it is surely going to decrease. If I'm here, it is surely going to decrease. But stochastic gradient method is not giving you the exact direction. It's giving you some approximate direction. But in that direction, I might increase, right? And then it's giving me some approximate direction in some direction like this, right? So it might be, so it goes like this. Okay, so what we really want is on average, right? What we are when we talk about these random. So now for us, the gradients are like random variables now, right? So now we can talk about expectation of this random variable. Okay, so is it true that in expectation, if I will actually get to the full gradient, so to the full. Okay, so in expectation, on average, is my direction close to the actual gradient? That's what we are talking about, right? So at each time I'm computing G1. So we can think of this as some distributions, and then it's generating some values, right? So does this distribution expectations, so on average, what value it takes? Does it take the actual gradient value? If it does, then it's a good method. Even though it's stochastic, on average you are guaranteeing that it will converge, right? So ideally, what we want is that the accumulated velocity or the gradient that we have should match the actual gradient. Okay, so G is the actual gradient, actual full gradient. So a stochastic method will be treated as a good method if on average the whatever gradient stochastic I am computing, if it is matching the actual gradient on average. So let us see what will happen, right? So V0 is 0 according to the atom rule, and V1 will be 1 minus beta times G1. Okay, so that's because the V1 will be, yeah, so V1 will be this, right? So V1 is 0 initially. So the V, so I mean the V is 0 initially. So V1 will be 0 plus 1 minus beta 1 and G, right? Let us say that is G1, right? Yeah, so that is G1. And then similarly, we do the computations. Vt at the Th step will look like this. Okay, so if you solve for that recursion, you will see that this is the pattern it will have. And now we apply the expectation. So expectation of the Vt. So expectation of a constant is just a constant. So constant just comes out of the expectation because of the linearity of expectation. So the expectation goes inside because beta is also a constant. So that will also come out. So what you are left with is just this, because only G is the random variable here. So expectation will apply on Gi. Now, if we assume that all Gi come from the same distribution, because it's like you are assuming some IID. So in that case, we know that expectation of, so this is a further assumption here. Okay, again, you can say that what is the guarantee? Well, there is no guarantee, right? Because the Gi that is being found here may have come from some other distribution and G2 may have come from some other distribution, maybe. Okay, but if we assume that the way these GIs are randomly being generated are coming from the same distribution, in other words, we are sampling from the same distribution, then then we will say that all the GIs are same, and let us say that is equal to some G, which is the actual distribution. Okay, so GIs follow some distribution G. Let us say G. G is the distribution, let us say. Okay, so what do we have here? So this means that if we take expectation of Vt, so this is so Gi, right? So Gi, I can so Gi is like a so since I'm summing over I equal 1 to t and all expectation of Gi are same, so so it can come out because I can take a common. So Gi can come out here. Okay, so it can come out. So Eg goes with 1 minus beta, and then remaining term is still the sum of beta t minus I. So these are the terms. Okay, and then what is this, right? So this is sum of the first t terms in a geometric series, right? So this is the formula of that is 1 minus beta t by 1 minus beta. So 1 minus beta gets cancelled. So what do we observe from here, right? What we observe from here is that if we take this guy and if we would have Vt originally itself by this term, we would have exactly got the expectation of the distribution actually. Okay, so that tells us that we should observe this guy here. So this will be, so if we divide by that, so this is expectation of Vt divided by, yeah, so 1 minus beta got cancelled. So this is 1 minus beta t. This will be expectation of G. Now, since expectation is a linear, so expectation is linear, so a constant can be observed inside. So this means that Vt divided by 1 minus T. Okay, and that will be expectation of G. So if there is any bias while choosing the Vt, those bias I will get rid of each time. If I do a proper scaling like this, then any bias that I'm introducing will be gone away, because each time the Vt, the new Vt will be Vt by this. So V tilde will be Vt by 1 minus beta t. That will be not varying from the actual distribution. Okay, so that's the bias correction that we see. So if you see the original term, so this is the bias correction that you computed V, you divide by this. then you are unbiased, because the expectation of your average is the actual average. Okay, so that's what we mean by unbiased estimator, right? An estimator is unbiased if the expectation of that mean, whatever mean we think of, in this case v tilde is our mean, so that mean matches the actual mean, which is expectation of g. Now same thing could be tried for this also, because this by symmetry you can see that these are like similar. So you may try to do that as well. Okay, why the bias was also like that for the a term. Okay, so that's the Adam method with the bias correction, and these are the plots. So if you indeed start from here, all do converge to the minima, and unfortunately I could not embed this thing here, animation, but if I remember correctly, Adam was the fastest. Okay, so Adam method is in general very good. So it's recommended to use Adam whenever you can. Okay, that's the overall conclusion of all this. And Adam also manages to go to global minima in this example as RMS prop and RMS prop with momentum and ADA grade. So it does not miss, at least in this example, it doesn't seem to miss the global minima. So there were some references also that you can look at for more like animations and so on for this are actually from here. Okay, so I have discussed the optimization problem, and what is really missing right now is how to compute the gradient, right? I have told you that you can compute the gradient of your neural network. So this is, let us say, the whole neural network can be seen as a function, so linear combination activation and so on. Now the question, a big problem in a neural network is, or there are many different types of neural networks. You have recurrent neural networks, you have convolutional neural networks. Okay, so and then like many. Okay, you have LSTMs. Okay, with attention models are there. Okay, so in all of these, you would like to use the gradient method or some variant of what we discussed, Adam method, let us say, and the main thing is like how to compute the gradient, right? That's not something we have discussed yet. We assume that the gradient is there, right? So the remaining part will be on how to compute the gradient actually. So this is the neural network that we have, and we can write it compactly in this form, right? So I can accumulate the weight vectors of the first layer as a matrix. Okay, and then I can accumulate the weights of the second layer like this, and then I also have the bias and so on, and then I can write this in a compact form. So this is the function of the neural networks, and it's a function of the weights and the features. Then I can do g of a2, right? So a2 here. So this is the output, right? So I can see this as, so this is the function g here I have defined. So g is the activation at the second step. So this is the g functions, g of this output, right? So g of a2, yeah, a2 will be these guys. Okay, so a21, a22, a23. So this will be g of W2 transpose. So I can see this as W2 transpose H1. Okay, so let us see this W2 transpose and H1. So H1 is here, W2 transpose is here. You multiply this, do you get these values, right? That's the question, right? So we do have, right, so W11 H1 1, right? And then we have yeah, so and then we have the second term also. So this will be a transpose first, and then we will multiply this, and you can check that after doing this, I get this these values as well. So I have expanded W2 A2 as W2 transpose H1 plus B2 because B2 is also there. So I have added also B2. Okay, and then H1 is G times A1, right? So I have substituted G times A1 here. And then A1 was W transpose this. So these are the A1, right? So this A1 value are there, right? So this is A1, and that is given as W1 transpose. So W1 transpose A naught, this one, right? So you can check that this sorry. So you can check that this is a kind of a nested function, right? So G, you can see the weights are also nested, right? And these are also your unknowns because bias are also unknown. So this is a highly nested function because I have stopped at the 2 layer, right? So there is W here, and then second layer weight W is here, then the first layer weight is inside G, right? So G of W transpose times G of W1 transpose times N odd, so on. So there is a nesting, right? So this is a nested function. And and for the gradient descent method or the stochastic gradient method, what I need to know is to compute gradient of the neural network. The actual would be the loss, and the loss involves W, right? And the loss itself will be some function of neural network and then the level, right? So a simple loss function I can construct is fn minus the level y, right? So this could be our loss. So if I want to compute the gradient with respect to W, I have to compute gradient with respect to f and n also, which is this guy. And you know that this is not that easy because of the nesting. Okay, so these are the difficulties in computing the gradient and applying the optimization solver in such complicated models. So this is how things are. So I have defined some loss function, and this is my neural network. And I am defining this loss over all the samples. So for each sample that goes in, the neural network produces an output, and then I check what is the output with respect to the actual level that I must get, and I define a loss over that. So this is the loss I'm supposed to minimize, right? And the W will be helpful in doing that. So I will keep changing the W in such a way the loss remains minimized. So this is minimization over W. So this is the optimization problem we have in hand. So SGD requires the gradient computations, and this is highly nested. And so this is the challenge one for the optimizer, is how to compute the gradients. The first challenge. Okay. The second challenge is vanishing or diminishing gradients, especially in deep neural networks and RNN. The another problem that we have are of vanishing or diminishing gradient. Because of the nested nature of this, I often need to compute gradients like this. Okay, so we will see this in the upcoming class, and if these values are small, then if I multiply all of the small quantity, I get a very small gradient, and then there will be no update because the gradients became very small. So overall gradient of the loss is very small. So we know that if the gradient is small, SGD will have no update. So these are another issues, especially in the deep neural network and RNN. Okay, and there are other issues. Challenge 3 for the optimizer is non-smooth objective functions. So for instance, if I choose the activation function as a non-smooth, for instance, ReLU. Okay, so ReLU, if ReLUs are like this. Okay, so this is non-smooth. Okay, so this is non-smooth, non-differentiable. So if I end up using this, then my neural network function will involve such nonlinear, non-differentiable functions. Okay, and overall the neural network will be non-differentiable or non-smooth. In that case, how will you compute the gradient? Because here the gradient is not defined. So these are the challenges we have, and we will try to tackle these challenges in the next class. We will see how to compute the gradients in such cases for neural networks, and then for let us say, if I have time, then I will see for RNN, how do we compute the gradient, because that is the main challenging part. And what do we do for challenge 2, which is the stochastic gradient, so I mean the vanishing or diminishing gradient, or there are cases where it can explode also, and then it will overflow. So what do we do for those cases? So I will discuss that. And non-smooth also I will discuss how to change the stochastic gradient methods to allow for non-smoothness. So this is something we will see in the next class. And then, yeah, so let us stop here. Okay, bye.